In this section, we're going to look at a topic called arc length in space for three-dimensional curves. And so arc length is just the distance between 2 points along a curve. So we've spent the last couple sections defining curves like this one here on the right. So this might be our curve r of t. That gives us every point along the curve for different values of t. And then the arc length that we're trying to find, which would be the distance between 2 points. Maybe say this point here is at t equals 0, so the initial point, and then we could define any point to be t equals t naught, and we would want to know this arc length, which would give us this distance here between those 2 points. So the general formula we use for finding arc length is this. So for arc length, I'll call that L. So we'll call it arc length L for length. So the formula is arc length is equal to the integral from a to b of the magnitude of the velocity function dt. And so these bounds on the integral here, a and b, those are just values of t. So your initial and final t values that correspond to the points you're trying to find the arc length between. Of course, this magnitude of the velocity function, that whole integrand, is just the magnitude of the first derivative of position. So that's what you plug in. And then you just evaluate that integral, and it'll give you a numeric answer for the length between 2 points along the curve r, so along this curve. So a pretty simple concept. Let's just try it out in example 1. So here in example 1, we're trying to find the arc length along the curve r of t on the indicated portion. So the portion we're looking at is between t equals 0 and t equals pi. And our function is r of t is 2 cosine ti plus 2 sine tj plus the square root of 5 tk. So the first thing I'm going to do is find the velocity function. So I'll just take the first derivative. So I know v is equal to dr dt, which in this case is going to be negative 2 sine ti plus 2 cosine tj plus square root of 5k. So we found the velocity function, the first derivative. Now we need to find its magnitude, right? We're constructing the integrand here. So the magnitude of v is just the square root of the sum of the squares of each component. So that's going to be the square root, and I'll leave it open because this might be kind of long, but of negative 2 sine t, that squared, plus 2 cosine t squared plus square root of 5 squared. And now because we have sines and cosines here, you might already be able to predict that we're going to be able to use that Pythagorean identity to simplify it to sine squared plus cosine squared. So let's simplify under the radical. That'll give us, what is that, 4 sine squared t plus 4 cosine squared t plus 5. And then from the sine squared and the cosine squared, I'm going to factor out the 4, and that'll give us 4 times 1, because I'm going to group the sine squared, cosine squared together. So that'll just be 4 times 1 plus 5, which is the square root of 3, or the square root of 9, which is just 3. So the integrand of our integral is just 3. So we know arc length, L, is going to be the integral of 3 dt, where the bounds of our integral, right, a and b, up here, those are our t bounds, the two values of t that correspond to the points we're trying to find, the length between. So we'll just go from 0 to pi. So that'll just be 3t evaluated from 0 to pi. And then plugging that in, we just get 3 pi as the arc length. Okay, great. So now let's do example 2. So example 2 is going to kind of be the reverse process of example 1. So it actually is giving us the distance along the curve, and we need to find the corresponding points. So it's asking us to find the point on the curve r of t, a distance of 26 pi units away along the curve from a starting point of 0, 5, 0. And here's our curve. It's 5 sine ti plus 5 cosine tj plus 12t k. So first, let's begin exactly the same by finding our velocity function. So v of t is going to be 5 cosine t I plus minus 5 sine t j plus 12k. And now we can find its magnitude. So the magnitude of v of t. And we can kind of simplify this in our head a little bit from the beginning. So we know it's going to be 25 cosine t, 25 cosine squared t plus 25 sine t squared plus 144k. So I'm just going to do the same process of grouping the cosine squared plus sine, or the cosine squared t plus sine squared t together to get 1 from the beginning, and just get 25 times, corrected that, 25 times 1 plus 144. Yeah, so that will be the magnitude. And I don't know if that comes out to be anything. Let me just check on my calculator. 144 plus 25 is 169, which is the square of 13. So that actually just equals 13. Okay, cool. So now let's just set up our general arc length formula again. So arc length is equal to the integral from a to b of 13 dt. And what were we given? We were given what the arc length is. So we know this arc length is 26 pi. So we can plug that in for L. And then our bounds, we weren't given any bounds, but we know the lower bound. The starting point is 0, 5, 0, which corresponds to plugging in 0 for t. So this 0, 5, 0, that initial point corresponds to a t value of 0, t equaling 0. So we know our lower t bound is 0. And now we're trying to find the point 26 pi units away. So what we're looking for, we're solving for this value. We're solving for this t value. And then we can plug in the t value into our position function to get the point corresponding to that t value. So let's do this real quick. Whoops. So that becomes 13t evaluated from 0 to b, which just becomes 13b needs to equal 26 pi. So in this case, from here, from this formula, we know that b, the upper t bound, has to be 2 pi. Right, just solving that formula. So if we know b equals 2 pi, right, that's our upper t bound. Now, that's not our final answer because that's a t value, and it's asking for the point on the curve, not the value of t. So now we just plug t value into r of t, the position function, to get point. So that's what we're going to do here. So now we're just going to evaluate the initial curve function, and we're going to evaluate that at 2 pi. So let's just plug in 2 pi into our initial position function, and we'll get 5 times the sine of 2 pi, which is 0. And then we'll get 5 times the cosine of 2 pi, which is 1. So we get 5. And now we have 12 times 2 pi, which just gives us twice 12, 24 pi. Let me zoom in. And so now we've found the point exactly 26 pi units away along this specific curve from an initial point 050. So you can use the arc length formula both in, like, I guess you could call example 1 the forwards direction where you're trying to find arc length, or in example 2 the backwards direction where you're given arc length and you're trying to tease out what the final point is. So that's kind of everything about arc length. The other topic covered in this section is an idea called the unit tangent vector. And so the unit tangent vector is kind of a special vector. It's a special vector on a curve tangent to it. So it's tangent to the curve at a point. I'll call that point T naught. And it has, you can imagine from the name, the unit tangent vector, it has length 1. And the notation we use for the unit tangent vector is typically, it's called capital T with the vector hat. So that's the notation I'll use for denoting it's a unit tangent vector. And you might take a moment on your own to pause the video and think about what this formula is for the unit tangent vector before going on and I explain it to you. Because you know everything now to construct it yourself, knowing that it is a vector that's tangent to a curve and has length 1. So it kind of combines two ideas we already know. So a unit tangent vector, capital T, is equal to, right, it's the velocity vector, because the velocity is always going to be tangent to the curve, but it's not necessarily of length 1, and so the way we normalize it is dividing by the magnitude of the velocity vector. So it's v of t divided by the magnitude of v of t. And so if I just draw a example curve over here, so I'll just do a little example. If I have some curve r of t that looks like this, here's r of t, I'll pick just any point. I'll pick this point to be t naught that we're evaluating at. In this case, if the curve is going in this direction, right, as t increases, you go this way, then we know the unit tangent vector is going to be a vector pointing in the direction of motion, tangent to the curve. Let me make that more tangent. So there's capital T. And we know that this length here, the length of the vector, is going to be 1. So it's just 1 unit long. Now, if you just have the generic velocity function, then this is a generic unit tangent vector function. And so you would have t's inside the unit tangent function, and that would just tell you you could plug in any value of t, and it would give you a specific unit tangent vector for any point along the curve. So there's both the generic version and by plugging in specific values of t. So let's look at example 3. It's asking us to find the general unit tangent vector function for this curve, and then find several specific unit tangent vectors for different values of t, and sketch them on a plot of the curve. So just immediately looking at this curve, this should be one you recognize. And this is why I covered it 2 sections ago of curves you should be familiar with. This curve is that unit circle curve, right, where it starts at the point 1, 0, and it traces out the unit circle going counterclockwise. So just to draw a sketch of it, to remind you, the curve cosine ti plus sine tj looks like this. Right, so plugging in 0 for t gives you 1i plus 0j. So your starting point is here. So that's at t equals 0. And then as you increase t, right, you reach pi halves, which will give you 0, 1. So you kind of just trace the unit circle. Ah, and look at that, that's beautiful. It fixes it for me. So here's our curve r of t. And then right as t increases past 2 pi, you just continue to trace over the unit circle over and over again. Okay, so let's work on constructing the unit tangent vector function for this curve. So first we need to find v of t. So v of t is going to be negative sine ti plus cosine tj. And let's get the magnitude of it. So that's just equal to sine squared plus cosine squared, which is just 1. So the magnitude is 1. So the unit tangent, the generic one, for any value of t, is just going to be, right, negative sine of t divided by 1, I, plus cosine t divided by 1, j. So there's our generic unit tangent vector function. And right, you could plug in any value of t, right, and that would give you a specific point on this curve. Well, any value of t would give you a point on this curve, and then plugging in that value of t into the unit tangent vector function would give you the unit tangent vector at that point. So let's try a couple examples. So I'll pick a different flavor here. So we'll plot some t's. So let's just try to begin with, let's just try plotting at the very beginning. So plot t equals 0. So in this case, right here at t equals 0, let's plug in 0 into our unit tangent function. So we'll get sine of 0 is 0, so we get 0 in the I component, and we get 1 in the j component, because cosine of 0 is 1. So this becomes the vector 0, I plus 1, j. Now this one's really easy to view, because you can see that it is of length 1. So you know for sure that this is a unit vector. And now let's just plot it on here. 0i plus 1j. That's just 1 in the y direction. So we get something that looks like that. Oh, I guess of length 1, it would be that big. So there's t for t equals 0. Right, and we can confirm it is a unit vector and it is tangent to the curve. Let's try pi halves. So plugging in pi halves puts us at this point on the curve. And then if we plug in pi halves into this function, we get sine of pi halves is 1, so we get negative 1 I plus 0 j. Now let's plot that at our initial point. So negative 1 in the I direction just looks like this. And that's for t equals pi halves. And then we'll do one more easy one. We can just, well, actually, let's try doing pi fourths just for fun. Let's try t equals pi fourths, just to get one that's not on not on one of the axes. So let's do t equals pi fourths. Whoops. So that's going to be sine of pi fourths is negative square root of 2 over 2 divided by 1. Right, so it doesn't change. In the I direction. And then we get cosine of pi fourths is also square root of 2 over 2 in the j direction. So we get negative square root of 2 over 2 in the I direction, and then square root of 2 over 2 in the j direction. So it's pointing negative in the x direction and positive in the y direction. So it looks like that, right? It's going negative in the x direction and positive in the y direction. So that's the unit tangent for t equals pi fourths. So you can see that this function is going to be true for any value of t, and it'll continue all the way around the unit circle, giving you vectors that are tangent to the curve and of length 1. So very useful. Let's try one more example. So it's asking us to find the unit tangent vector for the following curve at a specific value of t. So this one is not one you're going to have to know how to plot or what it looks like. So we'll just continue with the math. So in this case, v is going to be the first derivative of r. So we'll get just 1 I plus 2 t right to the 1/2. Okay. So we basically get the square root of t in the k direction. Now we need to take the magnitude of it. So that'll be the square root of 1 squared plus square root of t squared, which just becomes the square root of 2. Oh, wait. No, t, that actually ends up just becoming, yeah, t is not 1. So that becomes 1 plus t. There we go. T is not a number. I got confused for a second. So now we'll find our generic unit tangent function, which in this case will be 1 over square root of 1 plus t in the I direction plus square root of t over 1 plus the square root of 1 plus t in the j direction. And now let's evaluate that. Evaluated for t equals 8, right? Is that the value? T equals 8. So that's going to become 1 over square root of 9, which is 3. So 1/3 in the I direction plus square root of 8 divided by 3 in the j direction. So that is the vector 1/3 I plus square root of 8 over 3j that is of length 1 and tangent to this curve at the point where t equals 8. Now, I mentioned that this function is not one that you would have to know what it looks like or how to graph it, but something interesting to note just to build up your capacity to recognize what these functions kind of look like is that there's only an I and a k component. So we know that this function has to live in a plane, and it's the xz plane. So if I were to draw a little three-dimensional axis here, for x, y, and z, oops, how do I erase this? Oh. So because r of t only has I and k, you know that this curve is restricted to this plane. So the whole shape of r of t can only live in here. So it's not really three-dimensional. It's two-dimensional in the xz plane. So r of t, I don't know what it looks like, but whatever it does, it can only live here. So r of t has to be in that plane. And that's about all you would be expected to know or reason out from that equation.